Hello everyone, welcome to part 3 of my remastered tutorial on creating a digital audio synthesizer. In this part, we'll be implementing a way of controlling what frequency the synthesizer generates sound at based on what key's been pressed on the keyboard, as well as implementing an oscillator control that allows us to offset that base frequency for each oscillator that's generating sound. So to create a frequency independent keyboard, we're going to be referencing this Wikipedia page here, which shows us that every standard piano key on a piano relates to a certain frequency. So we're going to be sort of replicating this in our synthesizer, where we're going to do it through a hash map, since that's a logical data structure for mapping different values together. So for the first value, the key, we're going to be using a character, which will be what character we press on the keyboard. I'm going to map it to a frequency, which will be a double. We'll call this key frequencies, and we'll just initialize it to a new instance of hashmap. Now to fill these values, we're going to do this in a static constructor, just a static block. And we're going to want to define a few constants, a few local constants. One will be the starting key. We'll set this to 16. And one will be the frequency increment, or key frequency increment, which will be 2. Now what these mean here is on this Wikipedia page, it shows all the different keys and all the frequencies. Basically, all these different keys have a specific number assigned to them, and the starting key, which is 16, means we want to start at 16, this key here, which is a C2. I create the lowest key to be 16 because these really low frequency keys, they're basically inaudible, so we're not going to bother letting it take up space on the keyboard. The other constant, which was key frequency increment, is basically how many keys we're going to increase by when we're mapping the characters. So the jumps between, say, 39 and 40, it's only 20 Hz in this case, which is, if we include every key up to 88 or 108, then it'll just be taking up too much space on the keyboard. So I'd rather have bigger increments in frequency that are more noticeable due to the smaller keyboard space we have. And now I'm going to create a character array. This will be basically all the characters we'll be using in the keyboard. Call this keys. And we'll go from key Z all the way, including the slashes, up to the closed square bracket or curly brace. And then we'll create this char array out of this. Next, we're going to want to get a for loop. This is how we're going to map the keys to their specific frequencies. We'll start with an integer I set to the starting key, and a integer called key set to 0. We want to loop while I is smaller than keys.length, and that times by the frequency increment, the key frequency increment, sorry, plus the starting key. This is because when we're going to increment I by the key frequency increment. So if we don't times this by the increment we're incrementing by, it'll stop halfway through, or a third way through if we set this to 3, or a quarter if we set this to 4. And plus the starting key is because this is originally set to the starting key, so I want to create that room overhead so the loop doesn't close early. Now I will be increased by the frequency increment, key frequency increment, and key will just be incremented normally. So inside this for loop, we'll want to put a new key value pair into the key frequencies map, which will be keys of the current key in the index, and we want to create a new function here, a utility function, which will map a key number to a frequency, or create or generate a value using the algorithm up here, or the equation, which is frequency of key n is equal to 2 root to the power of 12 to the power of the key number minus 49 times 440. So we'll implement this in our utilities class, in our math class. So we can write this out as, we'll create a public static double, get key frequency, and we'll want a key number as the input. Now, if you know the Java math, the math class, or the static functions, there is no root to the power of. So if we do put, or we'll need to import static math, we'll just import everything as static. If we do, we'll put the power function, or return pow, because this is square root, or 2 to the root to the power of 12 to the power of n minus 49. We'll need to create our own root function, because the Java root functions, well, there is no root function, it's only square root. So we'll create another function here, call it just root. We'll root a number, num, and then a root. So number to the root of the whatever number we put through. So we'll return pow, just pow. The e constant to the power of log num divided by the root. So we'll go back up here, and we want to root 2 to the power of 12. And we want to raise this to the power of the key num minus 49. And then we want to times this result by 440. So head back into our mapping utility. We want to put utils.math, dot get key frequency, and we'll want the I value. So remember, this was originally starting key, so we'll want to generate 16. Want to get the frequency of key 16, which will be processed through this algorithm here, or the equation, sorry, and then placed into the map. After this for loop, we can just call every key value pair from the hash map. I'm not sure what the actual key value pairs are, but we'll put key frequencies here. Dot keys, or the value set actually. So it just wants a collection of doubles, so, and then we can print these. Now this should print all the mapped frequencies. You can see here, we're starting at, these seem to be in a random order. Let's see if we can find ones. 2637, which is this one, 0.02. 164, which is there, and 92, for example. So this basically means that all the keys have been successfully mapped to whatever character they've been assigned to. To make use of this new hash map, we're going to want to, well, first off, we can remove the loop that prints frequencies. We're going to head to the key adapter, so specifically the key press method, and we're going to want to loop through the oscillator array. And we haven't yet defined this method, this prop-it, but we want to set the frequency of O based on the key event. Next, we want to head over to the oscillator class, and the first thing we can do is remove the frequency constant, because we no longer have a constant frequency. Of course, this messes up some of the code down here, but we're going to fix this by adding 2 private doubles, the first one being the key frequency, and the second one just being frequency. I'll explain why these are different shortly. And to fix these errors, we can simply rename rename frequency to all caps, so it recognizes them here, and then rename it back to no caps. Next, we're going to implement the properties that we saw below, which will be get frequency, which will simply return the frequency, and the set frequency, which is going to do a couple of things. Just pass the frequency parameter here. The first one being it's going to set the key frequency and the class frequency, the stop frequency, to the pass frequency, and then we're going to want to apply a tone offset. Basically, once we're going to implement a label here, which allows to drag an offset, a frequency offset, up and down which will modify what frequency the oscillator is generating at. What we can do for individual oscillators, more on this later. We're going to start this off by creating a new J label, which will be called tone parameter. And it'll be set to a new instance of a J label with the text OX or X.000. We want to set its bounds to, not border, set bounds. We'll give it something 165 by 65, 50 and 25, and then set its border to the utils dot window design dot line border. Now currently this does nothing, but we're going to add it to the form anyway, just so we can see its location. So now when we run this form, we should see there we have a little box here. This label is going to take the place of a dial or whatever other controls that normal synthesizers use, just because we're not looking to implement graphics here. This tutorial is purely about logic of the synthesizer. And below this, we're going to want to create a new J label called tone text. This is simply going to be a new J label that says, or has printed on it, just tone, just to describe what the parameter below it is doing. And we'll set this thing's bounds to just above the proper parameter that we'll be editing. So something like 172 by 40, 75 by 25. And then we'll just add the tone text control. And the synthesizer now looks like this, more clear what this box actually is. Next, we want to give the tone parameter some functionality. We're going to do this by adding a mouse listener. We want a new mouse adapter and want to override the pressed and released methods. The first one, which we'll be using, which will be the mouse pressed event, we'll want to create a final cursor, awt.cursor, and we're going to want this to be blank cursor. This is basically, we're going to be using this label, we're going to be clicking it and moving the mouse up and down, which is going to edit an internal value, which will be the tone offset, and it'll edit this text here every time it's changed. Basically why I want a blank cursor, just because it gives you that feel that, you know, we're editing a parameter and not just moving the mouse around, and it stops the mouse just getting in the way basically. It's not much of a big difference, but I'd rather have it blank than not blank. So I think the way to do this is toolkit.default toolkit.create custom cursor. We want a new buffered image, size 16 and 16. Buffered image dot type in ARGB. This is very AWT specific things, you don't need to know this by any means. There's plenty of AWT tutorials, we just want to create a default cursor, we're not interested in how it works. Blank cursor. We'll move this onto the bottom line just so it's not going too far out of our editor. And then we want to set the cursor to the blank cursor. And now we're going to want to save or store the location or whereabouts the mouse was clicked. We'll add this as a field in synth control container. We'll have a protected field. Int mouse. I just want this to be a point. Mouse click location. And we want to set this to the event.get location on screen. Now down to the mouse release event, we'll want to set the cursor to get default cursor, just to return so we can see the mouse again, because I don't want it to be gone forever. Next, we're going to want to create a new field. We'll call this will be the actual value we're modifying to this parameter, which will be an integer, not a double integer. It will be the tone offset. And we're going to want to create a constant up here, private static final, call it tone offset limit. It's basically the highest offset it can go up or downwards to. So it's to 2000. and we'll head back and add a mouse motion listener. Oops. Basically, the difference between this is that the mouse listener, the standard one, doesn't pick up obviously motion events, so it's things like dragged or move. We'll want the mouse dragged event to be in the motion listener, and in here we're going to want to decide if the mouse location dot y, so the up and down position, doesn't equal the get y on screen. This will be, if we don't go into this if block, this returns false. It'll mean we've only moved the mouse to the side, which is not worth processing in this case. We'll create a new boolean called mouse moving up, and this will be set to mouse click location dot y minus the current y on the screen is greater than 0. That is how we check which direction the y-axis has moved on. Next, we can test if the mouse is moving up and the current tone offset is smaller than tone offset limit. We're going to increment the tone offset, else if the mouse is not moving up, so it's moving down, and the tone offset is greater than the negative tone offset limit. So we can only go above, we can't go above or below the limit. Then we want to apply a tone offset, which we haven't implemented yet. Also, we can't forget to decrement the tone offset. And then we'll want to set the text of the tone parameter to x plus, we want to get the tone offset in decimal. So we'll do that using a private property here, a private double get tone offset, and we'll simply return the tone offset divided by 1000. Now you may be wondering why we don't just increment tone offset. Why don't we just set it to a double and increment it by 0.001 and decrement it by that? It's because if you work with floating points for a while, you'll realise that they don't really return exact values from addition and subtraction and such. Simply because the way they work, they can't be that precise, or we'd use them instead of integers. The reason integers are here because they don't have rounding errors. You'll need to look into some other specific tutorial to find out why they have rounding errors, but simply they do and we can't do anything about it. So we'll need to store them as an integer and just divide the integer by a double, which won't cause any rounding errors. So now, if we start the synthesizer up, we should be able to, here we can drag the tone parameter and it'll increase to its maximum value and its minimum, which will be all the way down. It stops here, we can't go any higher. Now it does print on some values a lower number of decimal places than on the other, simply because it doesn't have to print anymore. So we can simply change that by wrapping this in string.format in here, and we'll set the format to the %.3f, so simply 3 decimal places. So it will always print the 3 decimal places after the number. Example, say we go all the way back up to 2 again. Keep in mind I know it goes blank and then reappears above, but we're going to be fixing that next using the robot class. So there we have all the decimal places we need. Now we are going to want to move the mouse back to its original click position, and to do this we're going to go to utilities. We'll create a new static class actually called parameter handling, and in here we'll want a public static final robot of Java.awt class. Call it parameter robot. And initializing this can throw an exception, so I'll have to initialize it in a static block with try catch. So parameter robot equals a new robot, and in case it throws an error, we'll catch it. We'll throw an awt exception e, and we'll throw a new exception in internal initializer error. Cannot construct a robot instance, which will just crash the program altogether, which is what we want, because if we don't have a robot, the program won't work correctly altogether. Head back to the oscillator class, and we'll do this even if we haven't moved the y-axis, just so it resets the x position. So utils.parameter handling dot parameter robot dot mouse move mouse click location dot x, so where we originally clicked, and mouse click location dot y. Now when we edit the parameter, we should not be able to move the mouse whatsoever, so it doesn't appear, doesn't go blank. We can keep moving it infinitely without having to move the mouse back down as it hits the top of the screen. This is a little slow for offsetting the tone, so if you want a higher, or you want to go faster but you don't want as much precision, you can simply turn down the tone offset limit and the divisor here. And now once we play this again, we should find that it increases twice as fast, but I do like the extra bit of precision, so we'll just edit these values back to normal. Next, we're going to implement the apply tone offset method, which we've commented a few times. So we'll implement a private void apply tone offset, and in here we'll set the current frequency that the oscillator will be generating its samples at to the key frequency multiplied by math.pow 2 to the power of get the tone offset. Basically what this is doing is multiplying the original base key frequency that we've pressed to 2 to the power of get tone offset. So basically if we multiply anything to the power of 0, it'll return 1. So if we have no tone offset whatsoever, it'll just return the key frequency. So this times by 1, there'll be no change. But say we raise it to the power of 0.0001, well, we can try this ourselves actually. We'll print the frequency. So now every time we move the mouse, we should see, or first we'll have to actually call the method, apply tone offset here, and apply tone offset here. Also, we need to go back here and set the key frequency of O. Forgot to do that. Set frequency, or put set key frequency, and we'll set this to key frequencies dot get e dot get key char. So go back to oscillators, the oscillator class. We edit the tone parameter. Oops, we're currently getting 0 here, which is because we haven't actually set the key frequency yet. So remember, we need to press a key for the key frequency to be set on each oscillator. So once we press a key, let's try pressing Z. Then obviously the tone offsets have been applied here for the first oscillator only. Because remember, we're printing this for every oscillator that has its tone offset applied. But when we move this up and down, you should see that when we move this, it only prints, or it only applies tone offset in one oscillator. And you can see that as we move it down, the frequency decreases. Move it up, the frequency increases. Only by a small amount, but that's just what we want. And we've got the right amount of precision here to create very precise frequency increments. Now we don't just multiply the frequency by math.pow to get a tone offset, because if the frequency is set to a high value and then we decrease it down, it'll be a new value. We increase it up again, it'll be just a completely different value from what the original key frequency was set to. And if we multiply it to the max tone offset and then multiply it back down, we'll be getting all sorts of weird values that stray very far from the original key frequency. So you did hear, or you should have heard, the low frequency that we played when we pressed the V key. So how about we hear a range of frequencies now that include the tone offset. So I'll press Z. If you can hear that through your headphones, that was a very low frequency sine wave. But let's go right to the opposite end of the spectrum and press the highest frequency key we have, which is the closed brackets, or closed brace, or closed square bracket. Now a very high frequency, and let's go middle of the road. And now let's try offsetting a tone of one oscillator while pressing different keys. Now you will be able to hear a lot of crackling once we're playing sound and changing the tone. This is because when we're generating the samples in the algorithm, once we change the frequency, it alters the value to the point where it's out of the, basically it has a different position if you plotted it on a graph, which causes that gap in amplitude, which causes a crackle, which we don't want. And in the next episode we'll be adding wavetables as a replacement for just these all mathematical algorithms, which will fix that crackle and popping. But that's for a next episode. For now we can just play with all the different waveforms and different tones and frequencies we can play them at. Although the slight audio crackling is really unappealing, we've basically increased the combination of sounds we can make to almost infinitely. Feel free to play around with all the new combinations of waveforms and frequencies, and we can even hear what I find really interesting is the phase cancellation of the waves. If you know your physics, you'll know what this means, but now we can create also almost an LFO effect when we increase the frequency very slightly. You hear one of the sine waves cancelling the other two out. Something I find very interesting. This has been part 3 of my remastered tutorial of creating a digital audio synthesizer. Thank you so much for watching. As I stated previously, the next part will be creating wavetables and the theory behind them, which will prevent all that crackling of the audio once we change tones, and it will greatly increase performance. Not that it was really hindering us in any way, but it's always better to have a faster program. So thank you very much for watching, and I'll see you in part 4.